Welcome to the online course on pericyclic reactions and organic photochemistry. We are in module 34 now. In this module, we will consider a very important concept, namely photoinduced electron transfer reaction. When a molecule is excited to its electronically higher excited state, it can do many things. It can get deactivated to the ground state by emission or non-emissive methods. It can, for example, be quenched by another molecule to come back to the ground state. It can also undergo electron transfer reaction with a suitable substrate with appropriate oxidation reduction potential. It can either donate an electron if it is a donor, or it can accept an electron if it is an acceptor. We will define what is a donor and acceptor in a few minutes, but we will consider the various aspects of photoinduced electron transfer reaction in this particular module. Now let us consider this particular scheme. In this scheme, what happens is a molecule D, which is an abbreviation for donor. Donors are typically electron-rich compound like aromatic compound, olefin compound, amines, and so on. When it undergoes an excitation by absorption of photon energy, it goes to the higher excited state. From the higher excited state, when it encounters another molecule, which is an electron acceptor, which is deficient in electron, there is an electron transfer process that takes place. In other words, from the neutral donor excited state molecule, an electron is transferred on to the acceptor molecule, and since both of them are to start with neutral molecule, when an electron is transferred, you produce a radical. When the electron is transferred, you produce a charge also. So what you produce is a charged radical. In the case of donor, it produces the cation radical. In the case of an acceptor, it produces the anion radical by accepting an electron from the excited state donor. Now, the donor acceptor radical ion pair is what is usually produced initially. Then it diffuses into free ions into solution depending on the solvent polarity. One of the factors that will favor the electron transfer process rather than an energy transfer process is solvent polarity. Electron transfer process typically is favored by solvents of high polarity, like for example DMSO, acetonitrile kind of solvents are useful for producing ion radicals by photoinduced electron transfer reaction. Once the ion radicals are produced, now they are free to undergo two types of reaction. One, they can undergo chemical reaction to go to the product. There are several different types of chemical reactions this ion radical pair can undergo to go to the product, or they can simply undergo a back electron transfer, abbreviated as BET, back electron transfer, in which case the acceptor anion radical donates back an electron to the donor cation radical, and it produces the donor and acceptor in the process by wasting the energy of the photon that is absorbed. So back electron transfer is always an energy wasting process because it reproduces the starting point from the donor and acceptor is being reproduced in this particular instance. The energy using process is the product formation. We will see many examples of such reaction. Now in the second scheme, what we have is, instead of a donor, an acceptor molecule is excited, and from the excited state acceptor molecule, an electron is being accepted from the donor when it encounters an electron-rich molecule, and in the process of donation of an electron, the donor becomes the cation radical, and by process of absorbing the electron, the acceptor becomes the anion radical. The donor acceptor anion radical, cation radical that is produced can go to the product by means of chemical reaction, or it can simply undergo the back electron transfer reaction once again in terms of producing the donor and acceptor back, which is an energy wasting process. So there are two types of electron transfer process that we have seen. One is in which the electron rich compound is excited to the higher excited state. Another one, electron poor compound is excited to the higher electronic excited state. In addition to that, there is another process. The donor and acceptor molecules can form a ground state charge transfer complex. The dA written within the square bracket essentially represents a charge transfer state. So the donor acceptor in the ground state itself, it forms a charge transfer complex. Charge transfer complexes are finite species with the definite spectroscopic absorption bands, for example, which is not present in either the donor or in the acceptor. When you mix a donor and an acceptor, usually the charge transfer band is formed along with the charge transfer complex in solution. A typical example would be the solution of iodine in benzene, for example, is purple in color because of the charge transfer band associated with the benzene iodine complex. Alternatively, if you take a colorless solution of naphthalene molecule, tetracyanoethylene is an electron deficient molecule. When you mix them together, you get vivid colors because of the formation of the donor-acceptor complex, which is corresponding to the charge transfer band. When the wavelength of excitation corresponds to the charge transfer band, electron transfer takes place from the donor to an acceptor, producing the charged cation radical anion radical pair. Within the solvent cage, this is formed, so they are called contact ion pairs. This is according to the Mulligan's theory of charge transfer excitation. The specific excitation in the CT band allows the transfer of an electron from the donor to acceptor to take place, and here there is no excited state donor or excited state acceptor involved in the process. Directly the donor cation radical and the acceptor anion radical is produced. This of course can diffuse into the solution to free ions from which chemical reactions can take place, or it can undergo spontaneous back electron transfer to produce a charge transfer complex or the donor and acceptor. So the back electron transfer can take place by collision between these two, or within the contact ion pair, radical ion pair, it can undergo the back electron transfer process. Now, any molecule in the excited state is a better donor as well as a better acceptor. This can be easily rationalized by means of an energy profile diagram. The back electron process is generally a very spontaneous process. This also we will see in a minute by means of an energy profile diagram. Let us now carefully consider this energy diagram. This is either the donor or acceptor, doesn't matter. We can define a donor and acceptor only with respect to each other. So let us consider this particular diagram here. This is the ground state electronic configuration of the molecule. The two electrons are in the S0 state, for example. This is the highest occupied molecular orbital. This is the this is the first excited state singlet excited state of this molecule. Now, if you want to define two parameters which are important in defining the donor acceptor properties of a molecule, these are the ionization potential and electron affinity. Ionization potential essentially tells you how easy it is to remove an electron from the highest occupied molecular orbital to infinite level, which is the vacuum level, which is this particular level here. So the energy that is required to be put in the molecule to excite the electron from the S0 state to the vacuum level is what is known as ionization potential. Higher the ionization potential, it is difficult to ionize the molecule. Lower ionization potential means it is easier to ionize the molecule. On the other hand, this blue gap that is shown here between the vacuum level and the S1 level is the electron affinity. It is the energy that one needs to put in order to accommodate an electron in the S1 molecular orbital of the donor or acceptor, for example. So this is electron affinity and this is ionization potential. Now let us see what happens when we excite the molecule. We can excite either the donor or acceptor, doesn't matter. We don't have to define it at this stage. Excitation process essentially promotes this electron to the higher electronic excited state. So there is one electron in the S0 state and one electron in the S1 state now. Now if you look at the ionization potential, the ionization potential is energy is now reduced. In other words, it is reduced by a quantum of this gap, which is supposed to be the E00 gap. E00 signifies the gap between the 0 vibrational level of the S0 state and the 0 vibrational level of the S1 state. So the ionization potential is now reduced. In other words, the molecule is easier to ionize in the excited state compared to the ground state. So the molecule is a better donor in the excited state compared to the ground state, and this is what is meant by the donor is a better donor in its excited state than in the ground state. Similarly, an acceptor is a better acceptor in the excited state than in the ground state. Now if you look at the electron affinity of the molecule, this would correspond to the electron affinity of the molecule. The electron affinity in fact corresponds to the energy that is necessary to put the electron in this shell and not in this particular shell, whereas the ionization potential corresponds to removing the electron from this shell to the infinite or the vacuum level. So the electron affinity actually is increased for the molecule. So in the excited state, the molecule has a better electron affinity, which means it is ready to accept electron even better in the excited state compared to the ground state. So let us make this statement: a molecule, organic molecule in its excited state, is a better donor as well as a better acceptor. Now ionization potential of the excited state molecule is nothing but the ionization potential of the ground state minus the E00, which is this particular cap. In other words, the ionization potential plus the E00 of the molecule corresponds to the ionization potential in the ground state. So this expression can be easily understood if you follow this diagram. Similarly, the electron affinity of the excited state molecule is the electron affinity in the ground state plus the E00 value, which is this particular gap, that corresponds to the electron affinity in the excited state. So the electron affinity is higher in the excited state, the ionization potential is lower in the excited state of a molecule, which makes it a better donor as well as a better acceptor. Now, in order to identify the process of electron transfer, we have to define certain parameter like the free energy of activation for the electron transfer process. In the gas phase, typically the free energy of activation for the electron transfer process is nothing but the difference between the ionization potential of the donor minus the electron affinity of the acceptor. Now, if it is an excited state electron process where the excitation is from the excited state donor, the electron transfer is taking place from the excited donor, then you have to substitute the ionization potential of the excited state donor in the place of the ionization potential of the ground state donor, because this is coming from the excitation, this is coming from this process. Donor is excited first and then the electron transfer process is taking place. So in the photoinduced electron transfer process where the donor is excited, the ionization potential of the excited state donor is what matters. And if you substitute the ionization potential corresponding to this value here, ionization potential of the excited state donor is nothing but the ground state ionization potential minus E00. So that is the expression that one gets. So this is the expression that one uses for the calculating the free energy change associated with the electron transfer when the donor is getting excited. Similarly, when the acceptor is getting excited, for example, the electron affinity of the excited state acceptor is what is used, and this expression is what is true for the electron affinity of the excited state acceptor. It is the electron affinity of the ground state plus the E00. So that corresponds to this expression, which corresponds to the electron transfer free energy change of the electron transfer when the acceptor is excited to the corresponding electronically excited state. So these equations are important to understand. These equations essentially arise from this diagram in terms of defining the excited state donor ionization potential and acceptor electron affinity and so on. The overall free energy change for the electron transfer process is what is given in these expressions. Now let us try to understand how the electron transfer process take place. First, the photoinduced electron transfer by the excitation of the donor we will consider. Now a donor is the one which is easier to ionize compared to an acceptor. So the ionization potential, in other words the HOMO level as well as the LUMO level of the donor will be at a higher level compared to the acceptor. Acceptor has a larger ionization electron affinity. So this is the larger electron affinity compared to this one here. So the energy levels are placed appropriately to define the donor and acceptor. A molecule can be a donor or acceptor depending upon what is the counterpart. In other words, whether the ionization potential of the counterpart is higher or the electron affinity of the counterpart is higher makes its donor and acceptor with respect to each other. So I hope you understand this diagram being drawn in this particular manner, where the HOMO level of the acceptor is lower than the HOMO level of the donor. Similarly, the LUMO level of the acceptor is lower than the LUMO level of the donor. Now what happens when the electronic excitation takes place for the D? The electron is excited from this level to the higher level. So this is the electronic configuration of D star now. Once you have this electronic configuration, there is a direct downward jump of the electron into the acceptor LUMO level. In other words, this is a highly exothermic reaction. That is why this reaction is fairly spontaneous. So after the electron transfer takes place, the donor loses an electron, so it becomes a cation radical. The acceptor gains an electron, so it becomes an anion radical. So this would be the electronic configuration of the donor cation radical and the acceptor anion radical. Now the blue arrow indicates the transfer of electron from the anion radical of the acceptor to the donor, which will essentially produce back the starting point. So you can see here, in fact, the exothermicity or the spontaneity of the forward electron transfer is not as much compared to the back electron transfer. The back electron transfer has a much higher driving force compared to the forward electron transfer in terms of the electron transfer processes that are defined. Similarly, one can also define the electron transfer process when the acceptor is excited. So in this case, the acceptor is the one that gets excited. So the electron transfer is taking place from the S0 level of the acceptor to the S1 level of the acceptor. This is the electronic configuration of the excited state acceptor. sorry, this should be excited state acceptor and ground state donor. There is a mistake here. Once you have the excited state acceptor, now this is a spontaneous process of electron transfer from the donor to the acceptor, producing the donor cation radical and the acceptor anion radical. You can once again see the back electron transfer is represented by the arrow, which is blue arrow here. This is also a spontaneous process. In fact, this is more spontaneous than the forward electron transfer process. The back electron transfer energy wasting process essentially produces the starting material back by means of a transfer of electron from the anion radical of the acceptor to the cation radical of the donor. Now, the important parameter for the sensitizer is nothing but a compound which absorbs initially the electron energy of the photon, and in turn it transfers the electron to the acceptor or donor depending upon whether we are defining the sensitizer as an acceptor or a donor. What are the important parameters for a sensitizer is a singlet higher excited state energy, which will define the E00 value, for example. In other words, in this expression, the E00 corresponds to this particular gap, and is the same gap that is mentioned here as a S1 level energy compared to the ground level, which is a 0 level, for example. The other parameter that is important as far as the sensitizer is concerned, these are also electron acceptor sensitizers. So the reduction potential is extremely important. This is obtained from the electrochemical experiment. This is obtained from the spectroscopic measurement of the absorption spectrum of the molecule. And these two parameters can be experimentally easily obtained by means of electrochemistry as well as spectroscopy, respectively. The electron donors are molecules which have a higher electron density. Typically aromatic compounds, olefins and amines are the electron donor. Ethers can be electron donors, for example, because of the oxygen lone pair. And the parameter that potentially important for the electron donor is oxidation potential, which is highly positive in the case of electron donors. You can see these are highly negative in the case of electron acceptors. So these are the parameters which are extremely important for defining the electron donor acceptor process. Now, once the electron transfer takes place, in order to avoid the back electron transfer, you have to consume the donor cation radical and the acceptor anion radical. Some of the cation radical and anion radicals are spontaneously decomposed during the course of the electron transfer process, and such a decomposition will ensure that return electron transfer or the back electron transfer is suppressed. So it is advantageous to have productive photochemistry by fragmenting the cation radical or anion radical to compete with the energy wasting back electron transfer. These are some molecules which will undergo spontaneous sigma bond fragmentation, epoxides and cyclopropyl derivative, aziridine derivatives, for example. These are all examples where the three-membered ring strain is released by breaking this carbon-carbon bond to produce the corresponding radical and the cation center as distinct centers, 1-3 centers, 1-3 relationship of the cation and the radical center in these molecules. Dimerbenzene, hexamethyl dimerbenzene, for example, upon oxidation gives the cation radical. The cation radical is highly unstable. It spontaneously rearranges to the aromatic cation radical, which is the hexamethyl benzene cation radical. Similarly, 2,2-paracyclophane is oxidized to the corresponding cation radical. Because of the ring strain associated with this molecule here, the two benzene rings are essentially parallel to each other, and the distance being about 3.5 angstroms or so. This is a highly strained molecule, so the strain is released by breaking this carbon-carbon bond to produce the benzylic cation and the benzylic radical, which are stable at this particular configuration. This is nothing but the photodimer of anthracene. Photodimer of anthracene, when it is oxidized by photoinduced electron transfer to the cation radical, these two sigma bonds are cleaved. You get two molecules of anthracene, one as a cation radical, the other one as a free anthracene. So these are all examples of cation radical undergoing fast fragmentation process that competes with the back electron transfer process. In the case of anion radicals, tetranitromethane is a very classical example of an anion radical which spontaneously fragments to the trinithromethide anion and NO2 radical, for example. The reaction rate is so much so that you don't see this species even in the femtosecond spectroscopy. Femtosecond is 10 to the power minus 12 seconds. So this is shorter lived than 10 to the power minus 12 seconds. So this spontaneous process of fragmentation ensures the back electron transfer being suppressed in this system. Similarly, tetrahalomethane anion radicals also spontaneously fragment. Either a trihalomethyl radical and a halogen anion is produced, or a halide radical and the trihalo methyl anion is produced. It depends on whether it is chlorine, bromine or iodine. If it is a chlorine kind of a molecule, this process is quite facile. If it is bromine and iodine, this process is also facile, for example. Once the trihalo anion is produced, it further eliminates the halide ion to produce dichlorocarbene, dibromocarbene and diiodocarbene, for example. This is a classical way of producing the dihalocarbene by means of reducing the tetrahalomethane to the corresponding anion radical and then fragmenting it to the dihalo species. Here is an illustrative example of how to calculate the free energy change associated with the electron transfer process. The ionization potential is in the gas phase. If you are going to measure in the solution phase, the equivalent parameter is the electrochemical oxidation potential of the donor, for example. Whereas in the case of electron affinity, that is applicable to the gas phase, in the solution phase it is the redox potential or the reduction potential of the acceptor is what is important. So this redox coupled acceptor anion radical redox coupled reduction potential can be measured from the electrochemistry of the, let us say, the dicyano-benzene, which is the electron deficient molecule here. In the case of the naphthalene, which is an electron rich molecule, the oxidation potential can also be measured. It is 1.6 volt, for example, plus 1.6 volt with respect to saturated calomel electrode. This is minus 1.64 with respect to the saturated calomel electrode. Now this is excited, the naphthalene is excited to a higher excited state of naphthalene, and the S1 energy corresponds to 3.94 electron volts. In other words, the E00 value, the zero vibrational level of the S0 state to the zero vibrational level of the S1 state corresponds to 3.94 electron volt, which is roughly 90.9 kilocalories per mole in terms of the unit conversion taking place with the corresponding multiplication factor. This data corresponds to acetonitrile as a solvent. That is important because the overall electron transfer process in a solution phase is the oxidation potential of the donor minus the reduction potential of the acceptor minus the 0 energy of the excitation wavelength corresponding to the 0 energy is what is implied. And finally, because of the ion radicals are being produced, a Coulombic term also comes into picture, which essentially takes care of the ionic interaction between the cation radical and anion radical that is produced here. In the case of acetonitrile, the Coulombic term is fairly small. It is about 0.2 kilocalories per mole. Now this can be converted into kilocalories per mole. This also can be converted into kilocalories per mole. So the E oxidation of the donor is about 36.9. The E reduction of the acceptor is about 37.8 kilocalories per mole, for example. The E00 is calculated as 90.9 kilocalories per mole. The Coulombic term turns out to be 0.2. Overall, if you calculate these parameters, it is about minus 16.4. In other words, the electron transfer process, the free energy of electron transfer is minus 16.4, indicating that it is a spontaneous process. If you want to calculate the back electron transfer, now you have to take the electrode oxidation potential of the anion radical, which is nothing but the reduction potential of the anion itself in the negative sense, and the reduction potential of the cation radical, which is nothing but the oxidation potential of the neutral donor. In other words, this is reversed in the case of the back electron transfer. So that is becoming even more highly spontaneous. The delta G for the forward electron transfer, which is this electron transfer process, is only minus 16. It is spontaneous enough, but the back electron transfer is even 5 times much more spontaneous than the forward electron transfer. That is one of the reasons one need to suppress the back electron transfer, because otherwise there will not be any productive photochemistry associated with the photoinduced electron transfer process. Now let us look into some beautiful examples of reactions which are carried out by initial photoinduced electron transfer process. If you take Stilbene and treat it with a tertiary amine and photolyze it, in other words, the photolysis wavelength corresponds to the Stilbene absorption wavelength. In acetonitrile as a process, the amine splits into two in terms of adding across the carbon-carbon double bond, producing these tertiary amines in the process of, in other words, the amine is added to the double bond to produce these two compounds in this. How are these two compounds produced? That is explained in this mechanistic feature here. Stilbene is excited to the corresponding higher excited state, singlet excited state, which is the pi star excited state. In the pi star excited state, it's an excellent acceptor, because amine is an excellent donor compared to this one. So it accepts the electron, for example, from the amine to the excited state of the stilbene, producing the stilbene anion radical and the cation radical of the amine. Now proton transfer can take place from the methyl group or from the CH2 group. If the proton transfer takes place from the methyl group to the anion radical of stilbene, you will produce the corresponding benzyl radical as well as the CH2 radical attached to the nitrogen, for example. On the other hand, if the proton transfer is taking place from the CH2 group, then you will produce the corresponding CHR and the benzyl radical, which is same as the benzyl radical coming from here. Please try to understand these are charged radical species, and when they lose a proton, they become radical. In other words, the charge is transferred from the form of proton from here to here. So as a result of that, the negative charge disappears when the radical is produced. Since the proton is removed from the cation radical, the resulting species is a radical species. Now the radicals can recombine to give the tertiary amines that are shown as the product. This C and this C can recombine to produce this molecule. Similarly, this C and this C can recombine to produce this molecule. Since these are happening probably in a solvent cage, the solvent separation does not take place. As a result of that, this combination, for example, this two carbon-centered radical combination to produce the hydrocarbon does not take place efficiently, because it has to come out of the solvent shell in order to meet this partner, and that does not take place readily. Only these tertiary amine products are formed during the course of the photoinduced electron transfer process. Now, intramolecular photoinduced electron transfer process from the amine to the excited state stilbene is what is represented here. Excitation corresponds to the stilbene wavelength. So after the excitation to the corresponding singlet excited state, electron transfer takes place from the nitrogen to the stilbene double bond. So the cation radical of the amine is produced, anion radical of stilbene is produced. The proton is transferred onto the center here, producing the benzyl radical and the amine N radical, nitrogen radical. This loses a hydrogen to produce the amine. In other words, one hydrogen can be transferred from here to this position here, resulting in the formation of a saturated system. In other words, you have hydrogenated the double bond in the process, producing an amine as the final product in this particular case. Alternatively, if the chain is long enough, the molecule can undergo cyclization at the diradical stage, for example. So this is a 1,7 diradical undergoing a cyclization process to produce the corresponding 7-membered heterocyclic ring system in this particular case. So these are examples of intramolecular electron transfer from the amine to the stilbene, producing the cation radical pair within the same molecule, followed by thermal chemical reactions taking place to produce the products that are shown in these schemes. Now there is another mechanism that can operate. If the stilbene is excited, for example, in the presence of a dicyanobenzene as an acceptor, then the electron transfer process will be between the stilbene and the dicyanobenzene as the acceptor in this particular case. In other words, stilbene is donor as well as a sensitizer here. 1,4-dicyanobenzene is the acceptor here. So the excitation process takes place to give the stilbene excited state, the S1 state of this stilbene. From the excited state of the stilbene, it undergoes now a electron transfer. The stilbene acts as a donor now, donating an electron to the dicyanobenzene process. In the process produces a stilbene cation radical and the dicyanoanthracene anion radical. Then the amine is nucleophile now. This is an electron deficient species because it is a cation radical, whereas this is an electron rich species. So essentially nucleophilic attack, the double bond takes place to produce the corresponding cation radical, followed by a deprotonation process is taking place to produce the radical. This radical now undergoes a electron transfer process from the anion radical of dicyanobenzene, and electron is transferred here to produce the anion here, regenerating the dicyanobenzene as the starting material is reproduced here. This is protonated by the amine to the corresponding hydrocarbon, which is this particular hydrocarbon. So overall, the amine is actually added across the carbon-carbon double bond, but the mechanism is entirely different from the earlier mechanism. In the earlier mechanism, the stilbene acted as a acceptor, amine acted as a donor. In this particular case, because of the redox potential which is favorable for this electron transfer, the stilbene acts as a donor and the dicyanobenzene acts as a acceptor. So this is one way of describing it. In this reaction, The dicyanobenzyne itself can be used as an acceptor as a sensitizer, for example. In other words, this is photolysed. Initially, the wavelength corresponds to the photolysis of dicyanobenzyne, which accepts an electron from the amine, for example, to produce the corresponding cation radical species. That mechanism is explained in this particular case. The dicyanobenzyne is excited, corresponding wavelength is used to excite specifically this molecule to produce the excited state, which is a singlet excited state of the dicyanobenzyne. Dicyanobenzyne accepts an electron from the amine to produce the amine cation radical and producing the anion radical of dicyanobenzyne. The amine cation radical is electron deficient, whereas stilbene is electron rich. So cyclization can produce the benzyl radical, and the corresponding ammonium salt is what is produced. Return electron transfer from the dicyanobenzyne anion radical to this radical produces the carbanion center, benzylic carbanion. Then the proton transfer essentially produces the molecule that is shown here. So the production of these two molecules based on the amine cyclization can be explained on the basis of the electron transfer from the dicyanobenzyne from the amine to the dicyanobenzyne, which is the excited state sensitizer in this particular case. The sensitizer is always regenerated in the catalytic cycle if you look at this. For example, in this case also the sensitizer is this is regenerated. This is also sensitizer is regenerated during the course of the return electron transfer process. The cation radical can also be trapped by a nucleophile such as alcohol. In this case, methanol is used as a solvent as well as the alcohol trapping agent. So essentially the methanol adds across the carbon-carbon double bond in a anti-Markovnikov's pathway, for example, to produce the corresponding methyl ether of the diphenyl ethyl methyl ether is what is produced by the addition of methanol across the carbon-carbon double bond. The mechanism is simple. Dicyanoanthracene is excited to the higher excited state. The diphenyl ethene is oxidized by the excited state anthracene to produce the corresponding anion radical of the dicyanoanthracene and the cation radical of the diphenyl ethene, which is trapped by methanol, which is a solvent here, to produce this cation radical. Deprotonation gives the radical. Return electron transfer from the anion radical to this radical produces the anion itself, which is quenched by a proton to give the corresponding final molecule that is shown here. So the simplistic way of explaining is shown here in the form of a mechanistic detail of this particular reaction. This is an example of a photo-cyclo addition process. When phenylvinyl ether is taken and photolysed in the presence of cyanonaphthalene, cyanonaphthalene is the one that is absorbing the energy of the photon. So the excited state process essentially corresponds to the cyanoethylene. In the process, it produces the 2+2 dimer of the phenylvinyl ether, the cis isomer as well as the trans isomer. How does this reaction take place? Excited state cyanonaphthalene is quenched by the phenylvinyl ether, producing the corresponding cation radical and the anion radical of cyanonaphthalene. It reacts with another molecule of the phenylvinyl ether because this is an electron rich process. A carbon-carbon bond formation takes place, producing the the cation radical, which is the 1,4 center cation radical. This is stabilized by the oxygen lone pair here, and this is stabilized again by the oxygen lone pair. This is a stable cation radical. It essentially forms a cyclobutane derivative in the form of a cis isomer as well as the trans isomer. This cation radical has to accept an electron from the anion radical of cyanobenzene. This is like a back electron transfer after the chemical reaction is over, producing the product, and the sensitizer is regenerated in the process of back electron transfer in this particular instance. Here is an intramolecular version of the cyclization of alkene. This enol ether is electron rich in nature. Dicyanoanthracene is, most of the cyanoaromatic compounds are used as sensitizers in many of the photoinduced electron transfer process because they have good characteristic features as far as the redox potential and the excited state energies are concerned. That is the reason dicyanoanthracene, dicyanonaphthalein, dicyanobenzene, tetracyanonaphthalein and all those things are used as sensitizers. So the cyclization essentially re-encloses this carbon-carbon bond here, producing these two ketones. The way to explain the formation of the two ketones, the mechanism is what is given here. Dicyanoanthracene is excited and it transfers an electron to the dicyanoanthracene, producing the anion radical of dicyanoanthracene and the cation radical of the enol ether. In the presence of a nucleophile like a solvent methanol or something, the trimethyl silyl group can be removed to generate the corresponding radical. This radical can undergo a 5-exoteric cyclization to produce the corresponding CH2 radical, for example. The CH2 radical is now accepting an electron from the reduced dicyanoanthracene to give the corresponding anion, which is protonated to give this particular methyl group here. Alternatively, the cyclization can initially take place to give this cation radical. Then the loss of the trimethyl silyl group as a cation, for example, produces the corresponding diradical species, which is accepting an electron from the anion radical of dicyanoanthracene to produce the 6-membered cyclized product. So this is a direct olefin ring closing reaction. This is a radical addition to a double bond 5-exo radical addition to the double bond. Resulting, this is a radical center. There should be a dot on the CH2 here. This is the dot has merged here. This should be on the CH2 here to show that this is a radical center. That radical center is reduced by an electron obtained from the dicyanoanthracene anion radical, followed by protonation to give the corresponding methyl species in this particular instance. This is a fairly nice example to show that this kind of a Lewis acid mediated cascade cyclization can also be triggered by electron transfer mechanism. Sensitization is done by 1,4-dicyanobenzene, that is a sensitizer. In other words, this molecule will undergo oxidation, reduce the 1,4-dicyanobenzene to the corresponding anion radical. The cation radical undergoes rapid cyclization, which is a cascade cyclization to produce a steroidal kind of a system. Finally, the cation is trapped by water to give the corresponding hydroxy species at this particular junction. In other words, you generate a cation radical here, which will undergo cyclization essentially to produce a radical here and a cation here. The cation is trapped by water to produce the OH here. So you can see this one carbon-carbon bond, another carbon-carbon bond, this is one more carbon-carbon. 3 carbon-carbon bonds are produced during the course of the cyclization, cascade cyclization from this kind of a species. This can be cyclized under Lewis acid conditions, under protonation conditions also. This is a demonstration of photoinduced electron transfer mediated cascade cyclization, which is also possible in this particular instance. Here is an example of a cation radical fragmenting and undergoing an addition. Dicyanoanthracene is the sensitizer. When it is excited, the tributyl benzyl tin undergoes electron transfer reaction, gives an electron to the dicyanoanthracene to produce the anion radical and cation radical of the stannane. The cation radical of stannane has a very weak carbon-tin bond, so it cleaves essentially to give the tin cation and the benzyl radical. The tin cation and the benzyl radical adds across the 9-10 position of anthracene anion radical to produce this as the final product. So you can see here the fragmentation followed by addition across 9-10 position essentially leads to the formation of the product. This is a sterically hindered molecule, so this carbon-carbon bond is a weak bond which can be cleaved under the cation radical condition. Here is an example, a triplet state mediated electron transfer coming from a quinone excited state is what is demonstrated. Chloranil is abbreviated as Ca. The wavelength that is used corresponds to the excitation of chloranil. Chloranil is excited to the corresponding first excited state. It has a very good intersystem crossing efficiency close to 1, so the triplet excited state is formed. The triplet excited state chloranil is a strong reducing agent. It is a strong oxidizing agent. It is a strong oxidizing agent. It oxidizes the donor to the cation radical. In the process, it produces the anion radical of itself. The cation radical that is produced corresponds to this donor, and this bond becomes extremely weak and it fragments to give the protonated dimethoxyphenyl ketone and the corresponding radical, because when the homolysis takes place across this carbon-carbon bond, the charge resides on one carbon and the radical center resides on the other carbon. Now proton transfer from this to the anion radical of chloranil produces the semiquinone radical. The semiquinone radical accepts another hydrogen atom from this particular species here to produce the reduced compound of chloranil, which is this particular compound over here, and in the process it produces 2 molecules of the paramethoxyphenyl ketone as the final product. So this is an example of a cation radical fragmenting. The pinochle is fragmenting to the corresponding benz hydryl radical and benz protonated ketone, which is a final product. Deprotonation essentially produces the final product as the ketone in this particular case. Now let us go back to the charge transfer excitation. According to Mulligan theory of charge transfer, direct excitation of the ground state complex should lead to the electron transfer process, and this has been proven by spectroscopic methods by looking at this compound cation radical anion radical pair using ultra fast picosecond spectroscopy, for example. And the productive chemistry can also be visualized if the donor and acceptor anion radicals are not stable. If they undergo further chemical reaction, then one can see the chemical reactions also. The classical example of a chemical reaction of a charge transfer complex is the complex formed between substituted anthracene and tetranitromethane. Tetranitromethane is almost a colorless liquid. Substituted naphthalenes are pale yellow colored compounds. When the tetranitromethane is mixed with the anthracene, deep red and bright orange colors of the charge transfer complexes are formed. So reversible formation of the charge transfer complex is what is implied by this equation. Now if the wavelength corresponding to the bright colors of the charge transfer complex is used for the photochemistry, the electron transfer takes place from the anthracene to the tetranitromethane tetranitromethane, which is a highly electron deficient compound, for example. It produces the cation radical of anthracene and the anion radical of tetranitromethane. Nobody has seen the anion radical of tetranitromethane even using fast time scale spectroscopy. Even in the picosecond time scale, it is not visible by spectroscopically. It spontaneously decomposes to give the trinitromethide anion and the NO2 radical. Now the radical combination at this junction essentially produces the benzylic cation, the corresponding valent intermediate kind of a cation. The cation is quenched by the anion. In other words, radical anion both are added across the 9-10 position of the anthracene to produce the corresponding product that is shown here. So this is an example of a charge transfer mediated spontaneous fragmentation of an anion radical followed by recombination of the radical and the anion that is produced by the cation radical to produce the product, which are stable products. The crystal structure of some of these compounds are known, so it confirms the formation of this kind of products. Another beautiful example of the polarity of the solvent that plays a major role in the contact radical ion pair dynamics is illustrated in this particular slide. This is a charge transfer complex between an electron donor, which is dimethoxybenzene, 1,4-dimethoxybenzene. The charge transfer excitation produces the 1,4-dimethoxybenzene cation radical and the anion radical of tetranitromethane, which fragments to give the trinitromethide and NO2. Now we have a cation radical, anion radical and a radical. Whether the cation and the anion will combine or the radical cation and the radical will combine will depend upon the solvent polarity. In solvents of low polarity like dichloromethane, hexane and so on, the ion pair Coulombic interaction is very high. So the ion pair collapses to give the corresponding trinitromethide substituted molecule, and HNO2 is eliminated in the process. On the other hand, in highly polar solvents where the ions are stabilized, it is a radical recombination that takes place, resulting in the formation of the nitro compound and trinitromethane as the byproduct formed in this case. So by choosing the solvent properly, one can either promote a cation anion reaction or radical reaction, which is illustrated beautifully using this particular example. This is an example of an electron transfer mediated photooxygenation reaction. Photooxygenation can be carried out in the presence of oxygen and a sensitizer. Here 9-10 anthracene is acting as a sensitizer. The 9-10 dicyanoanthracene is the acceptor and this diene is the donor. Photoexcitation of 9-10 dicyanoanthracene in the presence of this diene essentially results in the electron transfer from the diene to produce the cation radical and the anion radical of dicyanoanthracene. Dicyanoanthracene anion radical has the right potential to reduce oxygen to the corresponding oxygen anion radical, regenerating the sensitizer. Now the oxygen anion radical and the cation radical of the diene undergoes Diels-Alder kind of a reaction to produce the endoperoxide, which is the final product in this particular case. This is a nice example of how oxygen can be involved in the electron transfer process, giving the endoperoxide as the final product in this particular case. Now, when tetracyanoanthracene is used as a sensitizer, a totally different mechanism operates. Here, tetracyanoanthracene anion radical and the cation radical of this indene is formed, dimethyl indene is formed. However, the tetracyanoanthracene anion radical cannot reduce the oxygen to the corresponding oxygen anion radical. For example, the dicyanoanthracene can have the right potential to the reduction of oxygen to oxygen anion radical. However, the tetracyanoanthracene anion radical cannot reduce the oxygen to the oxygen anion radical. So the cation radical is trapped by methanol to give the product that are shown here. The mechanism is shown here. Initially, tetracyanoanthracene anion radical and the cation radical of indene is formed. Indene cation radical is trapped by methanol as a nucleophile to give the corresponding ether in the form of a radical. Now the radical is trapped by oxygen. Remember, oxygen in the ground state is a triplet oxygen, which is a diradical state. So that is trapped in the form of peroxy radical that is given. The peroxy radical is now undergoing an electron transfer from the tetracyanoanthracene anion to produce the corresponding oxy anion, which is protonated to give these two products in the form of cis and trans mixture of the product that are shown here in this case. So what we have seen in this module is the basic elementary concept of photoinduced electron transfer, the energetics that are involved in the photoinduced electron transfer, how a molecule can be a better donor as well as a better acceptor in its electronically excited state is illustrated. Then the three mechanisms of electron transfer, namely donor excited electron transfer, acceptor excited electron transfer, finally charge transfer excited electron transfer. The examples are given. Several examples of how cation radical can fragment to beat the back electron transfer process, as well as anion radical fragmentation beating the back electron transfer process is shown here. Several examples of electron transfer mediated chemical reactions are also shown in this particular module. This is a very important topic because photoinduced electron transfer is the primary process that takes place in the photosynthesis and solar energy conversion and so on and so forth. So understanding the basic concepts of photoinduced electron transfer is extremely important, and that is what we have done in this particular module. Thank you very much for your kind attention.